Okay, so firstly, hopefully you saw my email about the paper assignments that I have done. So let's see, how many students are here right now? 4, 3, 7, 2, 9, 12, 15, 18. And registrar office shows 26. So let me try a different exercise a little bit. These are the names that come up. So let's see. Do any of you see your teammates missing? Yeah. So who's missing?
11.
Huh?
Number 11.
Number 11. Okay.
I'm not on that list.
You are not on that list? You are not registered in the course?
So I wasn't here for the past few weeks, so yeah, so I'm not registered.
Okay, so you need to register. Okay.
And my teammate is
Not here.
21.
Your teammate is not here. Okay.
No, my teammate is in the class, but well, he's there, but not right now.
Right. That's what I'm looking for. Okay. Let's see. So I know Daniel is here. Andrew is here. Martin. Okay, there's Mark. Sian. There. Julian. There. James Harris. Okay. Anna is in the class. Okay, there she is. You're in the class. You're in the class. You're in the class. I'm in the class. There. And. Nope. Okay, 13. So let me scratch. Zhao, you're here. Okay. Michael Lowe, you there. Joseph Miller, there. Arliss is here. Matthew Nichols. You're Matthew, right? No. I'm just taking attendance. Oh, you're Daniel, right? Okay, so Matthew Nichols is not here. Mrunal Patel. He's in the class?
Yeah.
Okay. Jennifer is here. Edward Saad is your partner. Okay, Swapnil in the class. Brian is in class. Zayu is in the class, right? Yeah. Javed is in the class. Jishwan. Okay, that's you. Okay. So hang on a second. So why is my count going so wrong? Okay, so this scratches off potentially 2 people from the class, 24, and then we add 1 because you need to enroll in the class, so we should be 25. So we have 1, 2, 3, 4, 5, 6, 5, 11, 6, 17, 4, 21, and we are missing 2, 23, so there are a couple of more missing. Okay, you should contact me so that I can add you to the presentation list and all. Okay. Okay. Hopefully we'll figure it out. Who's not on this? But in any case, so it sounds like we may end up with 1 less paper than what's out here. So this was with 26. It seems like at least 2 people are no longer in the class, but we have 1 addition. So we'll adjust that. For week, I just want to make sure that we are okay for the very first one. It's very hard for me to. Okay, so a week from now, so I know Daniel contacted me, James here, I guess Hamza will know, Joseph, so everyone, as far as I can tell, is in class, so we are good to go. So the read the instructions in terms of the presentation and all, but for the reviews, the idea is I didn't want to swamp you guys with excessive reviews and all, so it's basically going to be 10 reviews over the course of the quarter out of sounds like 25 papers, and just to distribute them evenly, I've assigned students into groups, and then for each paper I have listed this group has to do. There is one day when there is a single paper and then everyone has to do it. And on the day you are presenting, you pick, so I've made sure that I've not, the paper you are presenting is not assigned to your group, but then you can just pick one of the other paper, so you don't have to do 2 reviews, just have to do 1 review. Okay, and we'll submit it using Gradescope. So that's how this part will work. Hopefully by this weekend I'll have all the other papers also populated. This first batch basically kind of relates to material that we covered in the first couple of weeks, so kind of more what are the attacks, what are the weaknesses, those kind of things. So the other thing is, as you go around preparing the presentation, perfectly fine if you want to reach out to the authors and see if they have slides for you to use. You can incorporate those material. Some of the papers are from upcoming conferences, so you may not have slides available from the authors, but you can try. The reviews, when you are doing, you'll see that the slide template which I have provided, basically it kind of asks for summarize the paper, what are the strengths, what are the weaknesses, and what do you think are potential directions for future work. What you need to do is, when you're doing the 2 reviews, create PDFs for both, merge the PDFs and upload it as a single PDF to Gradescope, because there would be a single assignment and Gradescope doesn't allow submission of 2 files. So that's what we are going to do for that one. Okay, so that takes care of presentation. The other thing, be on the watch out, I'm going to send out a little form asking for your team names and the URL to your GitHub repo, which should also have the GitHub pages in it. So that's the other thing. So what I want to do today is, firstly, I kind of rushed last time on some of the aspects of distance bounding, so I want to, let's go over that again, and then we are going to start another topic, which is side channel attacks. So which is basically by monitoring things about computer system, be able to make inferences about what is happening. There's one team which is doing a project in that space, and I'm still exploring if I can hand out an assignment so that all of you can get your hands dirty a little bit with that method. It's a pretty powerful method. But for now, I just want to touch upon a few things about distance bounding, which I glossed over last time. So again, recall the problem we are addressing is that we do not want one party, the prover, to pretend as if it is closer than it really is. Or another way of saying is that we want to provide verifier, an ATM machine, a car, or something like that, an assurance that the other party, the key or a human being, is within a certain distance, right? So that's so we want to upper bound it as no farther than this distance. And kind of a simple strategy, which actually surprisingly many systems use, is simply kind of send a message, heartbeat message, are you there? And the other party responds, yes, I'm there. That's utterly breakable. So kind of the idea is they estimate the distance by kind of measuring T1 and T2 and by 2, but it's breakable because it's predictable, right? So one message out of this is that we don't want predictability, because then the prover can jump the gun and thereby kind of cheat. So another thing to so anything which allows T2 to be effectively tampered with creates a problem for us, right? So prover can tamper with T2 by essentially not honoring the protocol of replying only after it has received the incoming packet. It kind of jumps the gun, and it can because it knows the contents already. So we take care. We seek to take care of this thing by saying, okay, we are going to throw in a message which cannot be predicted, and so we use a random number out there to do it. But then that takes care of that problem. But it still has an issue, which is that a collaborating party can, on behalf of the prover, so prover is actually far away, but some sort of attacker or a proxy closer can pretend it. So it's kind of like, let's say there is an automated attendance system, and then my friend kind of marks carries my device or kind of fakes it. So using this kind of collaboration or what is called as mafia fraud, these things can be attacked. So then the idea becomes that could we do it so that only one party can answer the question? So not only do we have a random number, but we also have some sort of a function which the prover can calculate, but the other party cannot. And we kind of saw how it could be done cryptographically, so kind of some sort of a signature. Maybe it can only be signed by a key which is burnt into the hardware on that one device. Maybe Intel burns it, so that way there is some sort of a unique ID associated with the hardware, which by going to the hardware we can say sign it, but we can't just replicate it. So it's not like I can extract that key and hand it over to my collaborator because that key is burnt into the hardware. So it's kind of like that secure hash function kind of thing, but baked into hardware. So we can certainly kind of do it, but there are so that apparently solves this problem. We get rid of the collaborating attacker, but it's not really, still not really secure. And the issue out here is the fact that computing this function f takes time. And also receiving the message and sending out, right? So there is this sort of pesky issue of the delay that exists, that in reality we have to, our protocol has to account for it. So in reality the estimation of distance really looks something like this: t2 minus t1 minus some delta p, which we know is the turnaround time that's taken by the protocol, and so we can subtract by the processing and subtract that out. And of course, this has to be known publicly because these are part of the standard, right? Any third party should be able to calculate it. The problem here is that a malicious prover can essentially, again, deploy a faster hardware conceptually. So its actual processing delay could be less than what this algorithm budgets for. And usually these standards are designed for to accommodate cheap devices and stuff like that. So there's a lot of slack in delta P. So a prover can do that, and even tiny delays like a millisecond translate into huge distances when we are looking in terms of speed of light. So there are so we need to somehow reduce this delta P, right? I mean, we need to reduce it down so that it's as little as possible. So first thing which is done, which you can do is you can say, look, instead of operating on kind of a big message and computing a function of that big random number, I'm going to do it bitwise. So every bit of my random number, so instead of sending out all of NV in one go, we are going to essentially send first bit of NV, the second bit of NV, third bit of NV, and we are going to do the operation. This prover is going to do the operation on each bit. It will send back that one bit response, and then we will assemble it together to get the whole response. So this way, hopefully, the bit level operation are faster. So we have reduced delta P down, and so again we have gained some control over this. But still not quite acceptable because the challenge still remains that some of these functions and all that we are talking about can still be computationally expensive. So can we do it even better? So the challenge that we face is the following: that remember, we want a function that only the prover can do and no one else can do, and that indicates some sort of function which is digital signature or some sort of things which involve some keys, right? I mean, something secret that only that party could do, but those are again sort of computationally expensive. So we somehow need to move that out of the processing path. So the trick is, what are the simplest computation functions you might think of bitwise? So there would be simple logic operations, so like XOR or comparison or selection, muxing basically. So you can think of some of these bitwise operations where, depending upon the incoming bit, your response would differ. So then the kind of the approach becomes that we are going to do these bitwise operations. So let's say, for example, just the XOR in this example. So a bit goes, we XOR it with something that this guy had, which was an initial commit. So initially it selects a number. It says, I'm going, whatever random number you are going to send me, I'm going to XOR it against that, but I commit to it. So I put that one in a sealed envelope, send a sealed envelope out here so that it's sealed cryptographically, so this guy cannot look at it. But I'm committed to that value of NP. And then we do a bitwise XOR between NP and NP, so hopefully this XOR operation is pretty quick. This guy now gets the XOR of NP and NP, but still doesn't know NP. And then what we do is, we, as a final step, we now cryptograph, we kind of send what the value of NP was, we reveal it and we sign it and we send it out, and now it can verify it, okay, and it can open the commitment box and kind of check against that. So essentially, prover commits to NP and later on reveals NP, and no one else can interfere, and meanwhile we have made these operations pretty rapid. So this delta P now is, each delta P is pretty tiny. So we got rid of that, and that's basically the basis of kind of this protocol, which is called as branch-SHOM. It basically combines these three phases. Now we still have a problem. So in this thing, so remember, we are getting the bit, and we have to do this XOR operation. Which sounds pretty simple, and XNOR, which is a comparison. The problem is, to do all of this, we still need to go through some circuitry on the receive side. So we have to, the incoming radio signal over the antenna, you'll have to amplify it, you have to filter it, you have to kind of detect the bits, go through sort of demodulation, A to B conversion, and all, and eventually you have the bits. And then the processor does the hardwire gate, does the XOR operation, and then it goes out. All of this still has some delay in it, okay? Tiny as it may be. Again, at speed of light, even microseconds is a huge amount of distance, particularly if a purpose is to log into a device or something like that. So that's one challenge. Another challenge which I skipped over again last time, and I'll go back, arises from the following issue, that to make wireless robust over long distances and all, we often send the signal out over a longer duration than is really needed. So those of you who may have done a communication course, you may have heard of this term called EB over N naught, which is essentially energy in a symbol or energy in a bit relative to noise, and higher the EB over N naught, the more reliably you can decode the signal, okay? Goes back all to kind of Shannon's communication theory. So one of the ways we make this energy in the symbol larger is to kind of stretch it out, slow signaling over a long time. Or in more sophisticated methods, we kind of, instead of sending, when I'm sending a bit, instead of sending a single symbol, I send a train of symbols, okay? So I kind of often referred to as chips, for example. So instead of sending a single one, I may send a code which, crudely imagine, I may replicate one many times. So what happens now is the following: when I'm trying to convey a bit, but I'm actually sending at the waveform level kind of really a long signal. And so now adversary has an advantage. That symbol, that bit I'm sending, since it's stretched out, if the adversary has a good receiver, it can examine the opening part of that symbol and immediately know what bit it is. And so it's essentially able to say, you know, it's a 1, I don't need to listen to rest of it, because rest of it is really meant for scenarios when we have a weak signal and stuff like that, right? So we are stretching that symbol out. So the concept then becomes an adversary sitting close to the prover, or just with a better, more sensitive receiver, can examine the signal early on and now know what it is going to be, whether it's a 0 or a 1, and then play it out. Okay, so now it can again get ahead. So in this kind of attack, leveraging long symbol lengths, essentially that's what the adversaries do, that they make use of the fact that we design communication systems to be robust, and in order to do so, we kind of transmit things over a long period of time. And so an adversary which can examine the opening part of that symbol can figure out what it is and then respond based upon that without waiting for the whole symbol to kind of come through. So even fraction of a microsecond can sort of benefit from that. So So unfortunately, back to our story out here, that challenge still remains, particularly when these ultra wideband radios, which is what are used for very precise timing, get used, because their characteristic also is that these they kind of use a train of pulses, or they spread the signal out over time quite a bit. So again, the adversary has some advantages out here. So ideally, what we want is, we don't even want to go through any of this thing. We want a very sharp symbol and not have to go through any of this also. So small symbol, whatever, short symbols, and don't even hit digital. So could I do some useful function without going all the way into digital? So can I do XOR right here, right at the internet? NV coming in, and I want to do it. Well, turns out XOR is pretty hard to do as is, but there is a way around that one can do, and that is called challenge reflection with channel selection. It's a long name, but basically the idea is the following: that I have an incoming signal, that 1 bit, right? And based upon that, I am going to respond either on channel 1 or channel 2. So I have access to 2 radios conceptually. I can send out on one or the other, and which one I'm going to send out to will depend upon what the value of this is. And that, so in a sense, I'm sending some waveform over C1 or C2, but which one I send out depends upon what the incoming bit was. So it's a little bit like XOR, right? One way of thinking of XOR is kind of as a multiplexer function. So that's basically what we're doing. We basically take a fixed waveform, nothing special about that, but then we indicate the XOR functionality by saying which outgoing channel I'm going to send it out over. That's why it's called channel selection. So essentially it looks like this, that I have the incoming challenge, okay, it has 1s and 0s, and then of course I have my own XOR, I have my own functionality. So I basically bounce this thing back, I reflect it back, but where I reflect it back, which channel I reflect it back on, depends upon the bit that I have. Okay, so I literally take the incoming signal and reflect it either on channel 1 or channel 2, depending upon what my random bit was. So now all I'm doing is I'm kind of controlling some sort of a switch, and that could all be done in the analog field. So actually you can do these things with like nanosecond type delay, sub-nanosecond delays. So no modulation, demodulation, whatnot is needed. So that's basically kind of, this is one realization of it, where they show that they can achieve it at less than a nanosecond. Interestingly, all this work was done by a group of computer scientists. This is not electrical engineers doing it. So just also wanted to, I know oftentimes students ask me, is it too much hardware here or too much software out here? These things are interdisciplinary. So I think we should just get over hardware, software and all. I mean, you should ideally be well versed in everything. So yeah, it's from a hardcore CS group which implemented this concept and later on commercialized it by getting, at that stage, hiring someone to make a chip and all, but kind of the initial implementation was all just boards. So very tiny processing delays, sub nanosecond. So a nanosecond is how much speed of light? Like 3 × 10⁸, so like 1/4 or something like that, right? Yeah, so it's pretty tiny, acceptable. Now we are in the range of acceptable security threats. So yeah, so that's kind of the long story behind this. So so things that you want are unpredictability. Only the prover should be able to generate the answer, and we want the processing delay to be as tiny as possible, because that also is a threat window. Okay, so yeah, so that hopefully completes the picture from last time. Okay, so next topic wanted to start on, well, hopefully cover it today, is physical side channel attacks. And basically what this refers to is that we seek to attack a system, which in our case would either mean extract some information or affect the functionality of that system, not by corrupting the program directly, not by breaking some crypto, but by some physical means. So computer systems, when they operate, they are in a physical world. They have physical signatures, they take time, they emit heat, they emit radio signals, whatever, electromagnetic interference, they consume power. There are all sort of physical effects that happen, and likewise they are susceptible to environmental factors like temperature and acceleration and humidity and all this kind of stuff. So could we somehow make use of that? So physical emanations of various type can reveal the functionality of the system, and not just a computing system, could be other things like buildings and cars and televisions and whatnot. We'll potentially can design against these emanations. That is, we can try to design a system so that our secret variables are not correlated with the physical emanations. So for example, if the time taken by the program is independent of the value of a secret bit, then I'm good to go. So we'll see some methods like that. What I guess hurts in this process is that some of the computational progress that is happening helps the attacker. So we'll see that this whole side channel attack, a lot of it is about data analysis, and so all these fancy machine learning methods and FPGA accelerators and all, they kind of help make the attacks more efficient also. Last time I talked about like how AES is very secure and all. Well, actually AES can be very easily broken under these attacks. It's secure in the sense of computational powers, but if you don't implement your system properly, then through side channel attacks it's trivially broken. And actually if you just Google for AES side channel attack or AES power analysis attack, you'll see lots of YouTube videos and all in real time they're showing it. So it's kind of pretty fast. You can basically decrypt the AES keys, figure out the AES keys. So in an academic context, at least, I mean, probably my guess is that the spy agencies and all probably have been practicing some things like these for quite some time. But in the kind of in the academic conference world and all, this guy Paul Cocker in the 90s had a couple of papers, one called timing attacks on implementation of Diffie-Hellman, RSA and blah blah blah, and the other one is differential power analysis. So the first paper basically is about the following, that if you look at it as a software program, then the delay between input and output is often a function of the precise value of the input, right? So I have a program, let's say it's a function, takes an input x, produces y. Normally we just care about is it a correct realization of y equal to fx mathematically correctly, and we kind of worry about bit quantization errors and those kind of things and all. But the other thing is that there is also the time it takes to compute y from x is in most cases a strong function of x itself. What kind of things do you think play into that? Why does the time depend upon the input value? Like when you write a program, where do you think the computational time ends up? What causes it to depend upon the input value?
Might be that underneath there is some sort of branch prediction or something going on.
Okay, so if I may have somewhere, if x greater than 10, do this, otherwise do that. So now, and the two paths are vastly different, so I immediately get to know whether x is less than or greater than 10. Okay, so branch. What else? Loops, yeah, exactly, right? Do it as many times as x is, right? And a lot of algorithms, either as many times as x or something, right? I mean, branch, divide by 2 and kind of iterate, right? I mean, those kind of things happen. And then some of the basic operators of processors in many cases are dependent on that. So particularly trigonometric function or whatever, so a lot of the floating point operations and all, we think of it as simply we write it in whatever C or Python sine of x. but under the hood they are complicated iterative algorithms and all. Some of the hardware functions in floating point units, like particularly division, is often done in an iterative manner. Also, a big culprit is that so the floating point numbers follow a standard called IEEE 754, I think, or something like that. It's kind of a pretty complicated standard, talks about how to represent floating point numbers and all. But it has some special cases of floating point numbers which are represented in the IEEE standard, but which are really, really very hard to implement in hardware. Okay, in particular, certain numbers which are very close to zero, doing it in hardware is pretty painful. So most processors make a choice between saying that, instead of implementing that super costly hardware for these numbers which may not occur that frequently, they do occur, but let's say rarely enough, then maybe I will just track to software and then have a software emulation. So your program may still think it's executing mul x, whatever, mul r1, r2, r3, something like that, but deep down, when it's faced with that, it actually is tapping into a software library that comes with the processor vendor or is part of the microcode, and it just sort of gets functioned there. So it would take a lot more time. So variety of reasons, and even just the first category of reasons, branches and all, to the extent that like there is this there's some of these benchmarks which float around about kind of functions that are commonly encountered for processing images and sensor data and all, and they typically show that the best case to worst case execution time across those benchmarks are often as high as like factor of 50 or so. So like, if you just take the input space and see what the distribution of the delay is through that function, then the best case timing and the worst case timing is several sort of order of magnitude difference, right? 1 to 2 order of magnitude. So these delays exist. Moreover, whatever code you are running, again, remember good security principle, we should assume adversary knows the code. Okay, so now obviously the adversary can analyze and identify places in the code where there might be such data dependent delays, and it can kind of zoom in on that. So that was the idea out here, timing attacks, and in fact people showed that you can extract keys and stuff like that, because oftentimes somewhere deep down they would have some function like, if they iterate through the key, and if they'll say, if bit number I is 0, go down this path, if it is 1, go down that path, and the two paths are of different length. So you immediately look at it, and one by one you get the bits. We showed the same thing with power. In effect, you can think of power becomes a proxy for is a fancier insight into timing, because it tells you not simply how much time something is taking, but it also gives you a signature. So you can easily identify things down. So this became a more powerful type attack. So people have applied it for all sorts of things. So like this whole community out there which tries to cheat, or depending on the perspective, exercise their right to freedom by breaking into satellite TV boxes. So essentially these satellite TV boxes operate on an encrypted stream coming from the satellites before the video comes over your screen, and so again they use crypto, and breaking into those keys has been kind of people have tried to do a lot, and you can buy kind of broken transponders like these on eBay and stuff like that. Just generally kind of also like some printer manufacturers provide some encryption things into their cartridges so that the printer will only work with a corresponding cartridge, or I guess more recently like Apple doesn't allow third-party fingerprint sensor and those to be hooked up, because I guess their rationale is about security and all, but you could also say they don't want a third-party market to occur. So there are all these businesses which essentially use methods like these, and usually the way they get broken are through these physical means. So essentially people break into the key and then they advertise the key on Reddit or whatnot to let others sort of make use of that resource. So how do these side channel attacks work? So there are basically a few key things that one have to have. Obviously, there has to be some information that is secret that you are trying to extract, and usually the secret information would be encrypted. So you could really say that the real secret I'm after is the key, because once I have access to the key, then everything else becomes open book. So, but in any case, there is some secret, and it could be in an FPGA, it could be in memory, it could be in the register of the CPU, but it exists somewhere in the computer system. There has to be some aspect of your system that correlates with that secret value. Okay, so what I mean by that is, when the system is running, then something about the system depends, some physical thing about the system depends upon that value. Okay, so if that key affects what computation I'm doing, then maybe the fan, maybe the voltage, maybe something about the system has to get impacted if I am able to, if I want to be able to discern it. And then that physical component has to emit some signal. Okay, it could be noise, it could be sound, it could be heat, it could be time taken, and any such thing. So there has to be some physical impact of it. Then we have to have a receiver for that emanation, so something which can detect that heat or whatnot. So it's literally just a sensor. And then finally, I need to have some algorithms to extract from that noisy, weak signal physical emanation that I'm picking up. I have to kind of extract the information. So look at it this way, this is like a communication problem, right? I mean, except I know the algorithm, but I don't know the stuff being transmitted. It's going through this complex channel with computation and stuff like that, and I'm trying to recover the value, right? This is precisely what we get taught in communication and networking courses, right, at the physical layer that's happening. So that's fundamentally what a physical side channel attack is. And then, of course, rest of the work really is about discovering different physical emanators and trying to understand them and developing algorithms and all for them. Okay, so time and power are just one couple of examples, but recent times a whole lot of others have emerged. Next week, actually, on Monday, there is a talk by a faculty candidate in ECE from Georgia Tech, and their group has been working on electromagnetic interference, basically EM fields that are emitted by these circuits. So to the extent that even for very fast Intel processors running at gigahertz rates, they are able to figure out, they are able to do things at the instruction level, what instruction is being executed. So that degree of granularity that they can get to. Sound and magnetic field and all whole bunch of stuff which is being done. So if you are free, I think his talk is at 11 to 12 in the Shannon room. So if you're interested, go attend it. I think so. It's one of the top groups in this space. So the source of the secret information, like I said, very typically people target the key, but it could be anything. It could be any variable that you care about. It could even be the system is reading some value from a sensor, and I'm kind of interested in tapping into that. Okay, so that's the source. Side channel modulator, like I said, is essentially anything which will emit a physical signal and whose operation is being impacted by the value. Interestingly, a lot of stuff our systems do now, to make them efficient, we make them dependent on the data value. So I'll give you some examples. If the system is doing relatively little work, we lower the frequency and the voltage in order to save power. If the system is doing relatively little work, in order to keep our computers quiet, we know it's emitting less heat, so we are going to lower the speed of the fan, and therefore the sound of the fan is a function of the computation that the system is doing. Depending upon the content on my screen, the screens are power managed. So LCD, anyone knows what's the difference between LCD screen and OLED screens?
Okay.
I didn't ask you. Okay, so yeah, anyone, like how do LCD screens operate versus OLED? Yeah.
I don't know like a dim idea, but
Yeah, high level. Yeah, like,
so,
yeah.
for LCDs, black pixels are like they have the same power as any other screen like pixels. While OLED uses black pixels.
Black pixel, okay, yeah. So the reason is not because the in LCDs the pixels don't emit any power. The LCD pixels are nothing but, think of them like little shutters. Okay, we can change the opacity of them. Behind the LCD is a big light source, which is just on, and I changed the for at the pixel level I change the opacity. If it's a color screen, I will have nearby pixels with red, green and blue filters, but kind of same concept. So what's happening is that I have a constant light source, and then I have this very low power LCD thing where I can at a pixel level change the opacity of. Now of course what this means is even if I'm displaying total darkness or total whiteness, it's the same power as you pointed out. So people started thinking, hey, can we save power? So one thing was maybe instead of having a single light source, I can have like a bank of light sources, right? I mean, and so I can, if there are a big portion of the screen which is totally black, I can just totally shut things off. Doesn't work very well. But OLED, on the other hand, are LEDs. Each pixel is an emitter. It consumes power, okay? And so when the screen is all black, naturally all the LEDs are off, and therefore they consume very little power. On the other hand, if the screen is white, then all the three color LEDs there are on, and therefore it consumes a lot of power. So OLED, we like them for a variety of reasons, including power efficiency, because they naturally modulate their power based upon the content of the screen. But guess what? That is precisely the problem we are worried about. So efficiency argues for modulating the functionality of a computer system based upon the content. Security argues for that, and by the way, there should not be the emanation from any of this should still remain constant. So we want the system to become more efficient, and yet we want it not to leave any signature that is externally visible, and that's where the challenge sort of comes in. So we'll come later on what kind of things one can do to sort of cope with it, but right now, then the side channel receiver, it basically has to capture that emanation, and that we know how to do very well. I mean, sensors have been around forever, and this is nothing but an exercise in sensing that particular type of signal, and then from that recover the so we need to have some sort of a detection estimation algorithm. Again, we study about this in various courses quite a bit. So what has changed changed in a way is that there are lots of settings where, unbeknownst to without realizing, we kind of become susceptible to these kind of side channel attacks. Okay, so for example, your phone's battery dies or whatever starts. You don't want to buy the genuine Apple costly battery, so you go to the shop and there is some El Cheapo battery that you can buy at half the cost. But these are smart batteries. They talk to your, they're not simply supplying juice to your phone. They can do all sort of other stuff, including they can measure the power, and they can have a radio built in, and they can send that information out. So now that battery actually is in a very powerful position. It can see how much power your phone is consuming and send that information out, and therefore can becomes this kind of a side channel. So batteries can cause this thing. You can even imagine fan, right? I mean, fans and PCs, right? I mean, modern ones have speed control features, and also they get a signal from the PC saying run at this speed and all. But that signal, you can also view it as the PC telling the fan something about the workload. So the fan can monitor that and then learn something about what the PC is doing. Okay, so the next question becomes, okay, fine, please batteries and fans can be malicious in this manner, but they still need to get this information out somehow, right? I mean, can they really send this information out? Well, in the past, one might have imagined it's pretty hard, but nowadays, I mean, it's pretty trivial to have radios and stuff like that that can exfiltrate that information. So, in fact, when a few years ago, there was this whole episode about Edward Snowden, who kind of released a lot of bag of tricks that NSA was using, including some of the things he had described were things like a USB cable where kind of just the cable head had a whole transmitter built in and all, so you are using what looks like a normal cable, but it's actually a full-blown monitor and transmitter, and you can buy some of these things. I've seen companies selling cable for the lightning connector on iPhones. Looks like an ordinary lightning connector, but if you open it up, it has a microcontroller and a radio and kind of an entire spying device. So shrinking technologies basically makes extraction kind of relatively straightforward. Of course, you will not be able to build a radio in there which can transmit whatever very high rate data and over long distances, but that's not what you have to worry about. As long as you can get it out even a few meters, just to the neighboring room, potentially you are free at this point. So it's doable, easily doable. Okay. So okay, so this particular notion of extracting information by side channels is, like I said, is itself not new per se, other than kind of the 90s when the academic attention turns toward it. So one of the first example actually of this thing was back from Second World War. So AT&T Bell Labs at the time, they used to make kind of all these secure communication machines. So they were basically like typewriter type machines. You type on it and it will automatically encrypt and kind of send it out. On the other hand, would be a decryptor, not too dissimilar from like the famous German Enigma machines and all those kind of things. So in this particular case, it turns out that every time the letter was pressed, there was a electromagnetic pulse which used to be transmitted, and using as this is out there, using an antenna and amplifier, they could be picked up to 80 feet away. So essentially, it was a known vulnerability and all, and or whatever, discovered vulnerability, and then you would shield and stuff like that, so that the signal. So there's kind of a internal paper around that. There's something called Van-Eck Phreaking, and kind of the idea out here is, so the older before our LCDs, people used to use so-called cathode ray tubes. Hopefully you guys are old enough to have heard of it, but this is basically the preceding generation of display technology, kind of the big fat tubes. Excuse me. And what people had shown was that, like, let's say if I'm working on my display, the emissions from it could be picked up, and you can actually reconstruct it. Some displays are very simple. This is an example where we literally are able to snoop on the contents of the display simply because the way these displays work, which is they basically had the scanning beam, and so kind of lot of electrical noise essentially gets emitted, and the way they are modulated, all of those signals were basically can be picked up nearby. Piracy, I already mentioned that, breaking into cable modem boxes, gaming devices, stuff like that. So all sort of side channels get probed and exploited in this. Excuse me. So oftentimes actually interesting things can happen to these devices when they are resetting. Another modality which people often use is that you deliberately induce a glitch in the power supply. So the device is operating, but you cause a glitch in the power supply, and then the way the device reacts to it reveals you a lot about the behavior. So people kind of try all these things, because one disadvantage that makers of these devices and all have is that unlike a computer which may be sitting in a data center, this is out there, easily physically accessible for people to probe and also hacks for all these kind of devices. Other examples. This is a more recent paper. So, what they make use of the fact is the following: that modern hard drives, the spinning disk variety, SSDs, they are designed to be. They basically spin at a very high rate, and then the disks have bits packed very closely to it. Long story short, they're super sensitive to vibrations. So they're really designed very carefully to kind of combat with these vibration-induced errors and stuff like that. But what are vibrations? Well, vibrations is nothing but sound. So essentially, these disks are also super sensitive to sound because sound induces vibrations, and then the circuitry in there is really designed to it. So what this paper does is, it basically converts the hard drive in a computer into a synthesized microphone. Essentially, the hard drive becomes the microphone because it's so super sensitive to it. So this is another example of kind of like a side channel. Hard drives, obviously, when they turn and all, then they also make sound. So that there's a reverse direction where a program inside your computer can send information out based upon these physical channels. You can use spinning of hard drive, blinking of LEDs, or even thermal channels. You can imagine my computer is not on a network, but what I can do is to send bits out. To send a 1 out, I'm going to run whatever infinite loop type program, jack up the frequency of the CPU, it will burn a lot of power, and that thermal signature will get picked up. And then if I want to send a 0, I'll kind of essentially go in very low speed, no option. So I can communicate very slowly using these physical means both ways, going in, going out. So physical channels abound. So in essence, what sort of the work in this space then explores is that extraction of information, and I guess extraction of so several scenarios. Extraction of secret information. So I have not been able to tamper with the software. It's doing its job. I know what the software is, but I don't know some of the secret values it's operating on, and my goal is to extract that secret value. So that's case number one. Excuse me. A second case, a second type of situation which occurs is I have compromised the software, okay, through the network or whatnot, or maybe not through the network. Let's say I convinced someone to put in a one-time malware in there through a USB stick or something like that. But this network is behind a firewall, or maybe it's even air-gapped otherwise, so I cannot talk to it. There's no way for my malware to send information out. But then I can make use of these side channels to send information out. So now I have a buddy, I have part of my malware has infected, and we are trying to communicate. So we can use these side channels to communicate in this manner. Third one is I can use the side channels to inject information, compromise the integrity of the software. But here what we are going to talk about basically is the first scenario, which is there's a program. I've not been able to tamper with the program, but I know the program, or I at least have a general sense of its algorithms, and that it has some secret values, and I want to know those secret values. So attacker wants to recover the key. So now there are different types of attackers you can imagine. There are passive attackers who are just going to listen to those physical emanations, and then based upon what they listen, they are going to decipher that key, that secret. And then there are, you can imagine, active attackers which can inject some sort of physical stimuli like heat the environment, create a lot of noise, whatnot. They can do something and then cause the system to be affected, and then make the attack easier. Okay, so those are called active attackers. Then how invasive you allow the attacker to be. Am I allowed to change something about the device? Am I allowed to run my own program somehow? Am I allowed to connect some peripheral and whatnot? And then also oftentimes these things, particularly military devices and all, they have tamper-proof packaging. They may have sensors to detect tampering and all. So the question here becomes, what degree of tampering am I allowed to do? Am I allowed to open the shield? Am I allowed to probe the pins on the circuit board and all? So there's various degrees of intrusiveness that you might imagine. So the simple attack scenarios are kind of like this. There is a device under attack, there is an attacker, and I'm basically just, without any manipulation of its environment or its software, I want to just listen to the physical emanations and make sense of it. On the other hand, in a more fancier setting, the attacker can manipulate the device, perhaps provide some physical or even informational input, and then observe how the device reacts in addition to those manipulations we are doing. So this obviously implies a higher degree of control, but maybe I own the device, maybe it's deployed at my home, so I can perhaps do all these things. So in active attacks, we kind of manipulate, perhaps even introduce faulty behaviors, like I said, glitch the power supply, heat it up, all those kind of things and all. So variety of different ways you can do that manipulation. So I mentioned supply voltage. Clock glitching is another one. EM transient injection. So the idea is my device, and I'm going to create a lot of electromagnetic noise around it, like could even be just run the microwave or whatnot. Laser. It turns out that if you heat these things and all with a laser, you can again induce behaviors, rapid heating, cooling, and kind of other circuit level manipulations and all. So there are variety of sophisticated ways. Some of it are also used by companies to reverse engineer their competitors' products. So there's a rich industry kind of out there. More common, or at least more easily doable, are the passive attacks, where the idea is we are not allowed to manipulate the physical device in any meaningful way. We are allowed to observe the physical emanations, and just from those observations, we are going to try to extract information. And what we are going to make use of is known physics, that how doing computation affects the physical properties. So the physical properties which typically get used, power consumption. As I've often mentioned, the amount of power the CPU is consuming depends upon a lot of factors, frequency and voltage for sure, but also specific instructions and things like that. Timing, heat emanation, electromagnetic emanation, both long-range variety, like the one which I had cited from that World War II example, where it was up to 80 feet, and then there are also very short-range emanations. Even these integrated circuits emanate electromagnetic things, but they can only be picked up right close to the die. So your probe has to be on top of the chip. But if you have the device with you, you can certainly do that. Photonic emanations in many cases. Sound, keyboard, beating on the PC, and other forms of probing that you could do. Like you can attach oscilloscope probe to one of the traces on your PC, for example, on your circuit board. So these are all examples. Degree of invasiveness, non-invasive to all the way to where you literally can put stuff on the on the metal on the chip, for example. There are companies which can remove the upper layers of a chip, the passivation layers, and let you probe to connections in the chip. To also, like there is work where you remove the cover of a chip and then you put a thermal camera on it, and a high resolution thermal camera, and then that thermal camera tells you how much heat different part of the chip is producing. And now you begin to get a map that which transistors are more active, which are less active, and you reverse engineer those. So rich set of things. Again, the simplest one is power, right? Your system operates on a battery or USB power supply. You can just put a $10 little board, even cheaper one, which basically measures how much power the system is consuming, and then just capture it on a oscilloscope or something and analyze it. So that's the simplest case to all these sophisticated ones. So long story short, then we have this rich taxonomy that exists of attacks. So active versus passive, and different degrees of invasiveness. And I've kind of given you lots of examples. And like I said, this is sort of used both for spying purposes and commercial espionage, those kind of things also, and of course academic research. So, but the basic idea behind all of these essentially falls at its core is very similar. One is we observe these side channels and then somehow extract information, and the additional one is we do something to coax the system into some operating regime where it normally won't. So essentially look for it and then examine them also, because oftentimes it's not the normal operation which tells us something, but it's the operation under faulty situations that tells us something. But that's kind of the basic thing that goes on. So that's the high level story. I want to talk specifically about power analysis attacks because I guess they are the easiest, they have been the easiest one to study in academic settings, and therefore are the most mature of the lot. So, so at its heart is about the fact that circuits consume power, and the power they consume is somehow related to what those circuits are doing or the operation they are performing. So most of the digital computers, digital systems that we use nowadays are built around sort of silicon with the CMOS technology. And the reason is so is because they are very robust to noise and all, and also because they consume very little power. Okay, so and the reason they consume very little power, so kind of this is silicon level view, but at a very high level, these circuits are basically two switches. These transistors, they are essentially switches. One of them, they're complementary. So, for example, this switch is open, as in disconnected if the voltage is low, and it's shorted if the voltage is high, and this guy acts exactly the opposite. So, in a very idealized sense, these are switches who have complementary behavior, and they're controlled by the input, and then you have power supply here, and you have your ground output. So what happens in this case? Well, the reason we have low power is because these switches are complementary, so at no point in time are both simultaneously on. Well, not quite true, because when my input changes, then the switches have to change their state, so there will be a tiny amount of time in which top switch is turning on, let's say, and the bottom switch is turning off, or vice versa, and so some current will flow. But in a stable state, no current flows, or almost no current flows. In reality, again, these are non-ideal switches, so they leak a little bit of current. Okay, so fundamentally, the property that these circuits have is that if nothing is happening, no new input coming in, inputs are stable, let's say we have stopped the clock and all, they consume, other than that leaking power, they really don't consume any power. And it's only when we have activity, that is, bits are changing, do they consume power because of that tiny amount of time when they're changing state and power flows. So that's nice, because we want a system to consume more power when we are doing more work, and less power than when it's consuming when it's doing less work. Now, what has also happened is that over time, in recent times, if you may, that leaking power has gone up as a ratio. So it used to be that we could basically say, the whole thing is effectively 0 power other than when it is switching. So now when we would say maybe, let's say half the power is that leaking power and the other half is the static power. So that's kind of the CMOS level story. So this whole power consumption you can think of as kind of this power energy which is consumed when some action is happening, when it is changing state, and the first two fall into that category. And then there is energy which is consumed because of the static reasons, which is basically leakage or other things in the system. It may not be, which may not even be silicon or CMOS. So big part of the power consumption is dependent upon dependent on the activity. So if we think in terms of kind of equations, if you may, so there is this term which is because while the circuit is changing state, for a little while it's short circuit and it's also charging capacitors. So the first two terms correspond to things which happen when a clock ticks. And then there is this leakage, and then there is this other stuff in the system. And if I think in terms of in terms of my energy, so energy would be power times the time interval. So we basically just multiply it. So this term basically says if my program takes n clock cycles or n instructions, this is the energy it is consuming. Okay, so this is kind of really a function of my program. So in this guy, here I have delta T, so the energy which is being taken, even though this term was static, it's getting multiplied by the time. So it's okay. Long story short, what this says is that that a lot of parameters that occur in this system are in these equations are a function of the computation I'm doing. How many instructions my program has, how much time it takes, and this term alpha, which I kind of ignored, you can think of it as the probability that on a clock tick something happens. So like if I have a gate or logic gate or something, it's not the case that at every clock tick the bits change. So you can think of it as probability that on a clock tick something actually happens. Okay, so alpha is not going to be 1 every time something is happening. In a well-designed system, hopefully alpha is lower. But one thing which is obvious is that the computation that we are doing does affect the power and energy consumption. So if I'm able to monitor these things, I am learning something about the computation. And also I told you earlier that the computation, the time it takes, how many instructions are executed and all do depend upon the data values because of the branches and the loops and things like that. So I am indirectly learning something about the input values also. So different instructions and different data cause different switching. And in case of CMOS, what that effectively means is that power consumption does depend upon the instruction that is being executed, the data that is being processed. So if I examine the power consumption while the processor is doing an add or a multiply or a register move, they'll look different. Moreover, if I look at a multiply and when it's multiplying two arbitrary numbers versus a number with 0, they might look different. It depends processor to processor. Some processors have more uniformity, some are, you will see more distinctiveness, but at kind of a high level, this is largely true, provided you are able to examine with sufficient resolution. Of course, if your processor is running at a megahertz and you are sampling at kilohertz, then it's all going to be sort of low pass filtered out. So you need to have a high enough sampling rate, and you need to have sufficient number of bits to be able to see the differences that are happening. But if you can, then it's a reasonable hypothesis that my power trace and also the energy consumption over some window are going to be what has happened. So this is an example of 10 rounds of AES being done. So remember I said AES operates on blocks, and we kind of chop. Okay, so this is basically showing AES running, and you can clearly see some pattern, right? And firstly, you can clearly see that there were 10 rounds. Okay, I mean it's just so obvious. Okay, So by looking at the power trace, we can just eyeballing it. You can begin to get a lot of information. I can zoom in. So in this case, this is now one round of AES, and within that round, you see firstly there seem to be a couple of distinct phases, and then here you see different things happening at different times. So remember, these algorithms internally operate on multiple rounds where they convert the bits and all. So we are seeing the effect of those things out there. And again, by examining the code, again, let's assume you have access to the code and all, you can begin to say something about like what is happening out here, whether the key is 0, key is 1, those kind of things. And then this appears to be kind of the second phase, where kind of something like this. So looking at these traces, it seems like there's some structure to it, and they are not simply just arbitrary kind of things. So the very first thing to go around doing then is just visually inspect. You collect the data. Well, to collect this kind of data, all you really need is a storage oscilloscope, right? Scope which captures this thing, and then you are able to talk to a computer and extract this information. Nowadays, for pretty low cost, you can buy USB oscilloscopes which just let you capture stuff. So there are many different ways, and there are also dedicated boards you can buy on Amazon for USB. I have bought things for like $10. Alibaba Express usually has it even cheaper. They kind of just literally they talk to USB, and then they also monitor another USB line for power consumption and all. So you can do these traces super easily nowadays. Okay, so now by looking at these things, you can begin to get some sense. So for example, let's say it's a laptop, it's a higher end computer with caches and all. So when the program is running, if it finds the data value in the cache versus if it has to go out, there will be a big difference in the power footprint. In one case is going to the main memory, another case is just running off things. So you can begin to again learn something about the value. You see those repetitions and all, so you can begin to see how many loops there. One thing you can see is that it seems to be very easy to detect loops, which immediately suggests that if my secret somehow affects the loop count, then that's a bad idea, because it would be very easy to decipher that. So what's the solution potentially? One solution potentially is that the number of times you go through the loop should be independent of any secret. Likewise, if branches affect things, if there are two versions of it, my secret should not affect which branch I take. So begins to offer some guidance. So it's not as if your power trace is directly just telling you the data value is this. Okay, it's not like the bits are going over some bus and you are readily able to examine whether they were ones or zeros. You have all this indirect information, and then you sort of extract from that. So lots of like even sophisticated crypto algorithms and all get broken if you're not careful about your implementation. So in this particular case, it's the encryption algorithm underlying the RSA, which is one of the public key crypto systems, and in there they use essentially discrete log related functionalities. And kind of the idea out here is that the way their algorithm works is that between 0 and 1 there are very distinct differences which can easily be picked up, and so you kind of just eyeball it and you can begin to say whether you can literally kind of enumerate the bits of the key, because depending upon whether the bit was 0 or 1, it does something very different. Okay, so this is a case where presumably some sort of a branching is happening, and in this case the idea was if 0 it does a square, if 1 it does a square and multiply, and so you see kind of the difference out there. Sometimes you have to be more clever, and you may have to kind of do a little bit of searching to find what that hidden information. So essentially, your challenge out here is that the secret that you are after is latent. It's kind of hidden under the hood, and you are really seeing a very a manifestation of it which is very noisy, and between that variable and you is a whole bunch of computation. So it's not like you have a direct observation. So so a lot of times you may see just you're getting these indirect things. So by averaging over multiple readings and all, you can begin to get some insight into what is happening. So let me jump a little bit ahead. Yeah, okay. So so firstly, at a very high level, then things started out with what are called a simple power analysis, and that's the equivalent of I look at the trace, and like I was showing, you can identify loops and things like that. So when you are doing these kind of things, a very common approach that we often bring to bear is something kind of like a template matching, right? I will have a template when it does one operation, I'll have a different template when it's doing another operation, and then I'm going to do a template matching. So template attacks, basically what they do is that for each one of the cases, they would have a previously recorded sequence, and then you basically try to do a matching, some sort of a correlation analysis that you can do, and then detect it. There are challenges in this approach. Firstly, I need access to similar device which I'm trying to attack, and then be able to collect this profile, build up this profile, right? So if I have a device with whose code I know and who I fully control, I can, under different input conditions, I can operate it and then collect the traces and then build up a library, and then I can work it backwards, right? So if I have an algorithm, I can run it under different input settings, find these traces. So this way I could sort of begin to cope, essentially develop an empirical model. So for different parts of my function, I would say, okay, if the bit was 0, if the bit was 1, what does the signature look like? I capture it and I map against that. So that's one approach, but you could be smarter about it, because this approach of just experimentally collecting templates and all can be pretty painful. So what people rely on is the fact that all these different computational devices and all, they're kind of similar at some level. So maybe I can develop a parametric model and then fit that model to my device. So essentially I collect traces and then kind of fit my parameter model to it, and then use that model for my attack. So in that case, I don't need to know very detailed information and all about the device, but I could just operate from the level of this high level thing. So so there are lots of common abstract power models which get used in these things. So for example, there are models like the power depends upon how many bits are 1. Okay, so I could, or power depends upon some other attributes of things. So you kind of begin to develop simple models of how much power your algorithm would take under the secret that you have, and then develop things. So like for example, if it's a crypto operation, and since it operates on the keys, and the keys, and depending upon whether the bit in the key was 0 or 1, the branching will differ. You could think that some model like this might work very well, because if whether the bit was 0 or 1, it takes a different path. So my overall power consumption overall energy consumption over a time window would basically be a function of how many bits were 1. But other algorithms may have some more may require some deeper insight. So so the trick now is that instead of doing these templates and all, which can be pretty painful, you basically try to think of, for your algorithm, and given that you know the code and all, what's a reasonable first order model as a function of the characteristics of your secret, and then try to do a match with respect to that. So, yeah, there are various models that kind of are floating around for things like these. Simply eyeballing and fitting things, that kind of simple attack models, whether using these or template traces, is the first order type attacks. There are the more sophisticated attack, which is referred to as differential power analysis. And the idea in differential power analysis is that you try to be immune to, you try to develop immunity to errors or differences that may exist from device to device. So the challenge with template type attacks and all is, I may train on one device and now I'm trying to break a different device whose power consumption is somewhat different, because maybe it has more leakage in it, or maybe because the temperature was different. So there are all these confounders. So with differential power analysis, you basically begin to look at how the power differs under different input settings, and you kind of try to rule out what kind of the common errors that affect these devices. And then there is a category of attacks called higher order differential power analysis. So they kind of get more sophisticated, but deep down your problem basically is that given your knowledge of the device, given your knowledge of the algorithm, given your knowledge of how the physics operates, and now you are given a time series, and you have to tell me what the value of that secret was when it ran to the thing. So what would be the best match? What value of the secret will explain the observation that I'm seeing? That's really the problem that we are solving. So what can we do to combat this? So let's say you are implementing AES or any of these algorithms. What kind of measures you think can help us gain safety against attacks like these? Huh?
To alter the power consumption from some side process.
Okay, let's back up a little. Okay, so firstly I'm going to allow any type of countermeasures. They don't have to be program level, they could also be hardware level. Okay, processor level. Okay, so now let's discuss. Right, so our goal is that I don't want any information about the computation that I am doing, about the secret value to the one thing that you are saying is that I do dummy computation. Okay, so how would that help? Well, what would it look like? So like take the example of AES, right? We had multiple rounds of computation, and the round in a naive implementation, round depends upon whether the key was 0 or 1, key bit was 0 or 1. Okay, so that's how we are breaking it. Okay, so what would this dummy computation look like? Where will you insert?
So I think like the complete thing, like flags, spectrum kind of thing, like essentially hiding the signal below noise.
Yeah, but how would you do it? You're telling me what we want, but I'm saying how would you achieve it?
Insert some dummy code into your software so that when your processor runs that part, it's not doing the actual job, it is actually doing something else to confuse the attacker.
Okay, yeah, I think you're saying kind of the same thing that he's saying. So one thing I could do, for example, is that I could compute for both 0 and 1 every time, and then just pick whichever is the desired one. Hopefully that one instruction at the very end is simple enough and too fast to be detected, right? So I can always compute 0 and 1 and then pick one. So that could be one approach. Can you think of others? Excuse me. But that could be detectable.
I mean, what you want to do is asynchronous, isochronous computation, not allowing the attacker to see the timing.
Yeah, so I could try to make each one of those rounds have identical delays, but how? Like insert no ops? Is that, for example, what you have in mind?
Insert random delays as well.
how do you insert random delays? Right, I mean it's code. What are you doing exactly?
We're just using like counter or data function.
But what's the processor doing during that time?
Just counting.
Just counting. But that may have a very unique signature. Can you think of something you might do at the board level?
Maybe we should do.
No, shielding doesn't help. That's supplying power, right?
You can add a shielded, like shielded in the sense that some chip which we can't measure, and on it only when A is being done.
Imagine it's a device which plugs to the wall via a USB adapter. So I can always cut it. So I can't just have a impenetrable thing with a self-contained batteries and all. Okay, so let's imagine it has a power supply and I'm allowed to put my power meter there. Okay. Say it again.
To the power supply, you get like random power noise.
Yeah, but how do you do it?
Some
So the problem with adding the noise to power supply proposal is that you have to be careful that you're not adding noise into your circuit, because then the circuit will suffer, right? So what you have to do is you have to add noise so that any monitor external to your board is doing it, is facing it, but not you. But not, it's problematic solution. But I do see it. Okay, can you think of something along those lines better? Yeah.
You can just add a ton of capacitors.
Exactly, right? I mean, essentially, I'm adding if you add a capacitor, it's like a temporary charge storage. So I smooth out the signals, basically a low pass filter. So all this stuff that sort of spikes and all that you're saying, they'll just be smoothed out, right? I mean, so you can basically, put a big capacitor and then the external one is smoothed out and I'm safe. Okay, so that's a circuit, that's a board level solution, and a reasonable board level solution. Even a modest amount of capacitance can confuse the other party enough. Okay, all these other ideas you guys came up with, adding random computation and all, those are also all reasonable. None of them is perfect by itself. Okay, so can you think of something at the circuit level? What about it?
Make sure there's a constant supply and we maintain it at a high level. So try to get a flat wave, something that we will put up using the
Yeah, I mean, there's something you can do in that space, but I don't think you're hitting it. Okay, so actually, I think 2 or 3 weeks from now, there will be a faculty candidate from Illinois, and this is what he does. Okay, so modern computers have very fancy power energy management units inside them. Okay, and essentially one of the things they do is they control the frequency and voltage of the system based upon optimizing for power consumption and also thermal, kind of they control the fan and kind of the whole thing, the temperature should remain low and all. And for the most part, they currently do it purely to optimize for performance of the system. But what if they were to deliberately do it to fool the other party? So for example, okay, I do the regulation of the frequency, which is actually core to like Linux OS, for example, and all. I kind of add there that it's going to do, which will have some random component to it in an attempt to obfuscate what is the adversary going to be able to see. So I've seen that work. The only issue there is that it's acting at a slower time scale. So here we were talking about instructions and all. Those things usually operate, because they're dealing with more thermal things and all, they're operating at like tens of milliseconds. Okay, so just a different time scale, but the concept remains like that. You might imagine your capacitor idea or these kind of things can also be used if I don't want LADWP to snoop into my house. So I can put like a capacitor or or a rechargeable battery. So like a Tesla Powerwall, for example, I can put that and smooth out my home's power profile that the utility is able to see, and thereby prevent it from snooping inside. Okay, so you can do it. But circuit level, go even deeper. On chip, when you are doing these logic gates and all, can you think of some measure where you can design circuit for an adder or multiplier or an AND gate or whatever, which consumes same energy, same power, irrespective of what the inputs are? So it kind of goes back to something, the idea I said earlier on, which is do for both 0 and 1. Okay, so the idea, so what happens in CMOS, the way I shown was that there was an asymmetry. For some inputs, the bottom side is on, some inputs, the upper side is on, right? There's a class of logic which is such that there are like 4 paths, okay? There are 2 upper paths and 2 bottom paths. And always 1 upper path and 1 lower path are on. So the circuit, irrespective of the input it is seeing, always consumes the same amount of power. It's called DCVSL logic. Okay, it's twice as costly because it's twice the number of transistors, but basically to the first order it consumes the same amount of power and same amount of delay, irrespective of what the input is. So at the logic level you can also address these things. So all these levels you can address, right? You can add capacitors. I'm not quite sure how we'll get your noise idea to work, but at least in principle seems like a reasonable approach. I kind of shoot noise outside and make myself immune to it. Maybe we can get it to work. You can do it at the circuit level. You can do some stuff at the voltage regulation control level with the system operating system, and you can have your code, your application code, your algorithm designed in a manner where it takes constant time. So lots of work in recent times on compilers where I give it the code and it will generate the code, and the code will be compiled, will be constant time. Okay, it's very hard to be truly constant time because you still have effects like caches and all which come into play, but you can kind of try to achieve that. One community in particular where they are trying to do these things is for JavaScript and WebAssembly, which is a new version of JavaScript, these codes, because the problem there is the following: you have all these JavaScript and all come from various services that rely on your browser, and then they may be dealing with secrets like passwords and stuff like that, and your browser can snoop into it, or other things can snoop into it. So you're trying to protect that. One other thing that you could also do, which is not so much for power analysis but for time based things. So just like using capacitors and all, I can make the measurements worse. I can also prevent for timing attacks. I can prevent the attacker to measure time accurately. Okay, so like when it asks system for the time, the system deliberately lies about the time a little bit. Another method in the same vein which is done is the following: all these things that I talked about, instructions and all, there was an under the hood assumption that there was a clock tick and there were precise instruction boundaries. What if I were to have a clock whose edge I were to move around a little bit from clock tick to clock tick? Okay, so instead of a perfect, let's say 100 megahertz clock, my clock edge is a little bit earlier or a little bit later, and I kind of move it around, spread it around. So it's called spread spectrum clocks, whose purpose is to basically flatten out the emissions in effect, okay, that are happening. It not only helps with power a little bit, but actually it helps even more so with the attacks I mentioned where they use electromagnetic things, because essentially by moving the clock around you are flattening out that side channel. So hardware can help, code can help, compilers can help, OS can help. This is really a multi-layer problem there. So I guess I've discussed most of it. So constant runtime algorithms is your and constant control flow. So no branching on secret data. So you should make sure that whenever you are taking a branch, then the branch is not directly or indirectly a function of whatever you're trying to keep secret. One has to be super careful. Sometimes the branches are very explicit. If X, then do this. If Y, do that. But oftentimes you have implicit branching. Like, for example, you may do a table lookup based upon a secret data, and then make use of that value in further things. Okay, so you have to kind of trace through the code. There could be cache attacks where, depending upon what your secret data was, either I'm accessing something which is in the cache or not, and therefore the timing will differ. Okay, so lots of complicated things might happen. These kind of things, which some of you were suggesting, kind of like I just put dummy stuff and all. The challenge there is, in principle, they sound fine, and they will probably work if instructions all look the same. The problem is knobs look different than a multiply and add and all, so they're easily detectable and they can be thrown out. So simple measures, not too good an idea against good adversaries. Let's see. So people design crypto. So a lot of effort in people who write libraries and all of crypto algorithms and all is to make things constant runtime and all, so that the obvious attacks like power analysis and all are not successful. Other things you could also do is kind of at a higher level. You can say that, look, my implementations are going to leak the key and all, so I'm not going to use the key for long. I'm going to frequently update this thing, update the keys and all. So that's other kind of system level approaches that you can kind of bring out. Okay, I think I've talked about the hiding in hardware. So this is an example of a circuit. Those of you familiar with how CMOS circuits look like. So this is an example where what happens is that this circuit always takes, instead of just taking X, it takes X and X bar. And instead of producing Y, it produces Y and Y bar. So it's what is called as a dual rail logic. It's taking both, every variable is carried both in its positive form and a negative form. And then in this case, I'm always producing the true output and its inverse also. The idea is that as a result, these circuits look like this. They have sort of two different pathways. Like if you see, I have a series out here and I have a complement parallel out here. So I really have like two back-to-back gates, and at all times, both something here and something on the left side will get activated, so that the overall power profile remains kind of constant. So these are called dual rail logic and all. The issue out here is they are expensive. So what you are really doing is you are paying off against more silicon area. And the other challenge is that even though they do all of this, there is still minor variations between, like things are not entirely symmetric, so there is still some residual dependence upon the data value which can be exploited. But in any case, there's a long history of designing, using these for like the crypto accelerators and things like that, so that you make the hardware implementations of the crypto more secure. Another thing you can do is to shuffle the computation. So if your algorithms allow it, you kind of create a randomization in a time dimension. So a lot of these techniques kind of depend upon me knowing that, as a attacker, knowing when the operation will happen. There's a particular sequence which is going to happen, or at a particular time, right? Operation follows an operation and so on and so forth. What if we break that assumption? What if we introduce some randomness in my algorithm so that in different runs, the pathway that it's going to take is going to differ for the same data value, but yield the same result. So this is the counterpart of other ways computer systems use randomization, like they put data variables in different parts of the memory, things like that. The same counterpart over here, that a lot of time our algorithms have that we can shuffle things around and yet have the same result. So if we could sort of make use of that somehow, we could put the adversary at a disadvantage, because now the trace looks different every time. Okay, so that's another. So insert random number of dummy operations, shuffle the operations, do combinations of these, but we kind of try to hide things in the logic of the program. So these are variety of ways where sort of people go around hiding things, but still it's a cat and mouse thing. But one thing out here is that it's very hard to write code which is not leaky from side channels, and this is why kind of when I said earlier also that you should use well-designed libraries for crypto functions, because they usually, if they're coming from a good source, would be written with all these issues in mind. And even then, I mean, a lot of stuff out there is just easily breakable. I think the reality still is that, I mean, if you are designing something to run on your laptop and all, power analysis is probably not your first order concern. Although, like I said, if you are putting third-party battery, watch out. I mean, these are depends on what your threat model is, right? I mean, I guess for a UCLA professor is fine, but if you're a CIA analyst, a totally different story. How many of you read the article about how Jeff Bezos's phone was hacked by Saudi Arabian thing? So this article came out just yesterday. So if you recall, last year, or I think late 2018, Bezos and his wife divorced because it had come out that Bezos was having an affair with, I guess, some TV correspondent here in LA, and National Enquirer had sort of scooped that story and all. Okay, and I think he had then so a nasty spat between them, but it turns out, so he was using an iPhone X. This is May 2018. Apparently at some event here in Los Angeles, he met the current, I guess, I don't know, king designate or whatever, the main power leader in Saudi Arabia, Mohammed bin Salem, with whom unfortunately I share my initials. He's called MBS and mine is MBS, okay, but in any case, so apparently they met at a party and they exchanged WhatsApp thing. They became WhatsApp friends. And the analysis of Bezos's phone shows is that after that, he received a video on WhatsApp from this MBS guy, and after that, the data outflow from his phone increased by 29,000%. Okay, kind of huge thing through Safari and Apple Mail. So. And apparently, and then he started getting these texts and all, which were suggestive that this MBS in Saudi Arabia, he knew some of the private details and all stuff like that. So apparently WhatsApp at the time had some known problems, and so that was exploited by malware which was infiltrated through the WhatsApp things, and then went on to do its damage. Now, if you think about it, one of the things Apple could do, or these device manufacturers could do, is have an extra layer of defense. So, in some senses, the whole software system is kind of a leaky system, right? I mean, obviously, these companies have good intentions, but there are bugs. Another thing earlier, a couple of days ago, was that Google had found some bugs in Apple's privacy controls in Safari, which were subsequently fixed. It's very hard to make modern software totally secure, bug-free. And so when bad things happen, there are all these side effects, like the Bezos episode showed, and cost him a divorce and quarter of his wealth and stuff like that. Maybe, and this is kind of the good part of power analysis, that some people use power analysis to detect whether the code on the device has been tampered with. So if the code has been tampered with, then it will leave a signature. in case of Bezos's device, if there is a 29,000% increase in outgoing data traffic and all, that will clearly have had things. Now, if the software was trying to detect it, then if it has been compromised, you can no longer trust it. But maybe the battery or some external sensor with a separate processor can play that role. So, so one of the things that people have been doing is to try to identify whether a device has been infected, whether it's in a pristine state or not, by these external means, which we know that a network attacker cannot compromise. So we kind of use these additional sensors to kind of do it. So I didn't touch upon that, but the very same ability to sense what is going in the computational state of the device can be used as a defense mechanism also. And the kind of work in groups sort of towards that as well. Okay, so I'm going to stop out here, and we are going to pick up another type of side channel next time we meet. Okay, and again, those of you who came in late, if you are listed as a presenter for next Thursday, please just drop me an email or a Piazza note saying that you are in the class and are going to present, because if I don't hear from you, I'm going to remove you, and then even if you're in the class, then you will lose those many points. Okay, so I have high degree of uncertainty about how many people are actually in the class, so I'm trying to resolve that. So see you guys next week.